All right, so we're moving on to the content. First, we want to talk about the definitions of acids and bases. So there are three main definitions that I'm sure you've heard of before. The most common one is the Arrhenius definition, which focuses on the concentration of H plus and the concentration of OH minus. This one's very simple. HCl is an acid, NaOH is a base because NaOH gives up its OH. HCl gives up its H. Very simple. Then there's the Bronsted-Lowry definition, which focuses on protons rather than specifically H plus and OH minus. If you know, H plus is a proton, so the definition of acid is actually the same in Arrhenius and Bronsted-Lowry, pretty much. But the difference comes in Arrhenius. The difference comes in bases, where in Arrhenius it says it's specifically something that has OH minus, whereas in Bronsted-Lowry it's more on a proton acceptor. Okay. And then lastly, it's Lewis definition, which is the most different and the least commonly used in this sense. And it focuses instead of protons on electron pairs as donors and acceptors. Okay, we'll go into detail in each one. Firstly is Arrhenius. This is the classic definition and focuses on OH minus and H plus. Acids are molecules that can increase the concentration of H plus in solution. Bases are molecules that can increase the concentration of OH minus in solution. Classic examples: HCl dissolves into H plus and Cl minus. NaOH dissolves into Na plus and OH minus. By dissociating and in a solution, you increase the concentration of H plus because at the start you had no H plus, you just had HCl and say water, and then once it dissociates, you have a lot of H plus. NaOH dissociates into Na plus and OH minus, so again, it increases the concentration of OH minus in the solution. The strength of the acid and base is typically dependent on how easily it dissociates. So for example, HCl dissociates pretty easily, so it's considered a strong acid and base, whereas something that doesn't dissociate as strongly would be considered a weaker acid or base. Okay, very simple and straightforward. Next, slightly more complicated, is the Bronsted-Lowry definition. This is probably the one that's most tested and the most common one that you'll be seeing, and it focuses rather on protons. So acids are molecules that donate protons, while bases are proton acceptors, right? And if you know, hydrogen is made up of one proton and one electron, right? Whereas we said in the Arrhenius definition, a proton is we use H plus. H plus means that you have one more proton than an electron, so that just means you have one proton. So it's essentially H plus is just a proton. And it's exactly the same as the previous definition. An acid is just something that gives up an H plus or gives up a proton or increases the concentration in solution. Bases, however, are a little bit different. A base is anything that can be a proton acceptor. OH can also qualify as that because it can be an acceptor, but there are other things that don't even have an O or an H that can also qualify. For example, CH3COH is a very common one that you'll see, a very common acid that you'll see. And it's an acid because the OH here or here can be deprotonated into COO minus and H plus, right? So this would be the same, and this would just become O minus, this would just become H plus, and this bond would be broken. Again, dissociation just like with HCl. And then this proton gets donated away. This, however, is a common example of a base, right? And the reason for that is because the NH2 can be protonated into NH3 plus. If you can see here, it has this lone electron pair, which means it can act as an acceptor, right? An H plus or a proton can attach onto here and now form a bond. And now you have NH3 plus, instead of NH2 on this end, right? And it still touches carbon. That can also, that's what's considered a base by this definition. Doesn't have any OH, it doesn't have any OHs, just like NaOH would, but it's still considered a base because it's a proton acceptor. And the way you can kind of connect these two definitions is in water. If you put a base into water, so for example, if you put this into water, if it's a strong enough base, it'll actually take the hydrogen off of water and it'll turn water into OH minus, and it itself will become protonated into NH3 plus. And in that sense, it could increase the concentration of OH minus in solution, right? By taking the H away from the water and turning it into OH minus. Does that make sense? Okay. Oh, and I do want to mention this specifically with this definition because this definition is the most common and most well tested. So if you notice here, we have the same exact molecules, the acid and the base. And when you just put them in solution together, they can work together. One gets deprotonated, the other gets protonated, an acid-base reaction. Right? Once a base is protonated, it actually becomes an acid. And once an acid is deprotonated, it becomes a base. So if you can see here, this is what happens when you deprotonate this acid, and this is what happens when you protonate this base. Now, if you look at it, this is now an acid because it can no longer accept any more protons. It's already full. But now it actually has an extra proton that it can give away, thus making it an acid. This, again, now has no protons it can give away because it already gave away all its protons, but it has this spot where it can accept a proton now, thus making it a base. So you see, once an acid deprotonates, it becomes a base. When a base protonates, it becomes an acid. A strong acid always has a weak conjugate base, and a weak acid always has a strong conjugate. A strong acid always has a weak conjugate base. A weak acid always has a strong conjugate base, and the same applies in the other way. The reason this is if you have a strong acid, so say, I don't know, HCl or some strong acid, and it gives away its H plus, it very easily dissociates and gives away its H plus. It's very happy to give away its H plus. Well, now it's a base. It's just Cl minus, which is a base, right? Because it's a proton acceptor, but it doesn't want to take back its proton, right? Because it was happy. It was very easy for it to give away its proton. It doesn't want to take it back. So it's not very good at it. The Cl minus is not very good at taking its protons back and acting as a base. Whereas if something's a weak acid, it's very reluctant to give up its proton. It doesn't want to give up its proton, but if you force it to give up its proton, it will. But it becomes a strong base because as soon as possible, it wants to take its proton back because it wasn't comfortable giving it away in the first place. So if you're a weak acid and you are forced to give up your proton, at the first opportunity given, you'll want to take it back and act as a base. And that's what makes you a strong base, because you very easily accept protons. Does that make sense? Lewis definition is the least tested directly. So the concept has a little bit of a different name, or the concept, or like the idea is the same, that you may know better. It's called nucleophile electrophile, if you remember from organic chemistry. The idea is essentially the same as in the Lewis definition, and it focuses exclusively on electrons rather than protons or H plus, OH minus. So acids are known as electron acceptors or nucleophiles, as you may know them, while bases are electron donors or electrophiles, as you may know them. For example, a Lewis base can be NH3 or something like benzene, right? NH3, we talked about why it can be a base, right? From the last definition, because it can accept the proton. Benzene, we usually don't think of it as a base, right? Because it's very weird, right? It's not a typical base that we think of, but it actually is a base because it can actually be an electron donor, right? Because it has the pi bonds, which it can donate as electrons, right? So if you know, remember, a benzene ring looks like this. So these bonds can actually, actually you may see it like this, it's like a circle. These bonds can actually be electron donors, right? So that's why it can be an electrophile. Whereas something, a Lewis acid, can be actually, apart from what we already talked about, something like a metal cation, like Fe3+, or something like this, right? These can actually be considered Lewis acids, even though you would pretty much never think of them as acids in like the normal sense, in the proton sense, because it just doesn't fit with the definition, right? Because they don't really have protons or H pluses to donate, right? Like you would expect, but they actually are acids because they are electron acceptors or nucleophiles.